here. From this point on, I'm recording, right? So even if you have an issue with the sound or what you can see and stuff like that, at least later on, presumably if this saves properly and converts properly, I should be able to post this to YouTube and you guys should be able to go back over this as well. Okay, so Tiffany, if you're still having problems, try quitting your browser, reopening your browser and logging back in again and see if that helps. Okie doke. Okay, so let me get started. Okay, so let me move this out of the way and let's see. Okay, so I'm going to take a look at this first problem from Chapter 8. A lot of these problems really covered material that we've been looking at over the past 2 weeks. So we're going to be reaching back a little bit to start off with. Okay, this first problem says among adults in the United States, the distribution of albumin levels is roughly symmetric with a mean. By roughly symmetric, I think they're kind of hinting to you that like you might be able to suspect that it's normally distributed, with a mean of 29.5 and a standard deviation of 9.25. I'm going to, for the moment, ignore the units because we're really, since we're doing statistics on this, and we're mostly going to be concerned about the numbers rather than real world situation where the units would be just as important to us. Okay, so the mean is 29.5. Standard deviation is 9.25. Suppose you select repeated samples of size 20 from this population and calculate the mean for each sample. Well, notice this is an unusual situation. They actually gave us the population mean and the population standard deviation. We rarely know those two things, right? But in this case, it's an exercise, and they've told us this. Now, suppose you select the repeated samples of size 20 from this population and calculate the mean for each sample. Okay, well, we know that the means, repeated means, sample means from this population of size 20 should be normally distributed. It's symmetric, or we're presuming by symmetric they mean normally distributed. And since the population is normally distributed, even though it's a small sample, less than 30, we would expect the means of the samples, the samples of size 20, to be normally distributed also. If you were to select a large number of random sample size 20, what would be the mean of the sample means? Okay, anybody want to hazard a guess on that? I mean, we take repeated means over and over again, repeated samples, find their means. What are the means of the means going to be? What does the mean of all those samples approximate? In other words, okay, that's going to be a population mean, right? Yeah, 29. Thanks, Rebecca. 29.5. The means are going to approximate the sample means. We take the samples. We expect them to be around 9.5 because that's what the 9.25. That's what the population is. So if we repeatedly sample, sometimes we'll get lower, sometimes we'll get higher, but we expect the average of those means to be 9.25. What would be their standard deviation? Well, in the interest of making you do your own homework, I'm going to open up a notepad here, and I'm going to say to myself, okay, what's the standard deviation for these sample means? Okay, so I'm going to take my pen here, and I'm going to say, see, hopefully this will work okay. There we go. And, whoops, oops. Okay, and my mean is 9.25. My standard deviation is, let's see, I'm sorry, the mean is 29.5. My standard deviation is 9.25. Okay, so if I take repeated samples from this population, expect my mean to be 29.5. Okay, now my sample standard deviation, my sample means, I'm going to give that a special name, call it standard error. Okay, my standard error, oh, I'm having a little problem here with my pen. My standard error is going to be equal to Let's say it's going to be equal to the standard deviation of the population over the square root of the sample size. For our purposes, I'm going to change that to that sample size to 25, right? So you can do it on your own for the actual homework. Okay, so if the sample size was 25 instead of 20, it's going to be 9.25 divided by the square root of 25, which is 9.25 over 5. Okay, or roughly about 2. Okay, so standard error is going to be about 2. So the range within which we would expect to find 95% of the sample means, if we had repeatedly sampled this population with a sample size of 25, 95% of the time, we'd expect to be between two standard deviations below and above the mean, or 29.9 minus 4, right? Two standard deviations with 25.5, or above two standard deviations of 4 above, or 33.5. Okay, we'd expect it to be somewhere in that range. You guys can be more precise in homework, and you can also use the right sample size, but that's basically what we're doing in that problem. That's kind of like what we covered a couple of weeks ago. How does the standard deviation in sample means compare with the standard deviations of the albumin levels themselves? Anyone want to hazard a guess on that? How does the standard deviation and the standard error, how do they compare? Which one's bigger or which one's smaller? Right? Well, we know standard error is going to be smaller, right? Because we're dividing by the square root of the sample size. Bigger the sample size is, the bigger the difference between the standard deviation and the standard error. If you were to take all the different sample means and use them to construct the histogram, what would be the shape of their distribution? Okay, somebody hazard a guess on the shape? We know it's got to be normal distribution, right? Thanks. Okay, thanks, Rebecca, again. So now it's a normal distribution, right? If we construct a histogram. Well, now let's think about that for a second. It's normal distribution, and if we take a big enough sample size, it really doesn't even matter if the original population is normally distributed. If we take large enough samples, the means of the samples are going to be normally distributed anyway. Anybody remember what the name for the theorem that describes that situation? What's the name of that theorem that we were talking about that tells us that if we have large enough samples, or if we have small sample and the population is normally distributed, or if we take large samples and the population is not perfectly normally distributed, we wind up with a situation where the sample means themselves are normally distributed. Right, central limit theorem. Thank you again. Okay. If you were to take all different samples means and use them to construct a histogram, would be shaped to two. We went through that. What proportion of the means of sample size 20 are larger than 33 milligrams per 100 liters? I'm going to do this with my version of this. My version of this, it was the standard error was equal to, I'm going to call it 2, round it to 2 to simplify it for ourselves. Okay, my mean was 29.5. My standard error was equal to 2. So I want to know what percentage of the means are larger than 33 milligrams. Okay, so 33 milligrams is going to be up here somewhere, right? So we want to know what percentage are above this number. Well, since we know that this is normally distributed. In this case, it's not. We know it's normally distributed not because of the sample size, but because we were basically told it was normally distributed by suggested normally distributed when they told us it was symmetric. Okay, we're going to use our z table to figure out what this percentage is. Now, since they asked what's the proportion of the sample means of the samples that are greater than 33, not what's the percentage of people in this population that are greater than 33, right? They could ask us two different things here. They could have said, what's the proportion of the people in the population greater than 33, right? Which would be quite a few people, right? Because it's 29, because standard deviation is 9.25. So 33 is not even one standard deviation above the mean. It's only about a third of a standard deviation above the mean. So that would be a lot of people, but it's much less likely to get that big a sample mean because we're averaging so many people. So I'm going to do it for the version we're working with, which is size 25. You can do it for the actual problem. So let's figure out what that is. So first thing I have to do is figure out what's the z-score of that value. So my z-score is going to be the difference between that value and the mean divided by the standard error. Okay, so that's going to be equal to 33 minus 29.5. Okay, over the standard error, which in our case, I've rounded it, but I'm going to call it 2. So that's going to be equal to, let's see, 3.5. Oh, 3.5 divided by 2, which is going to be equal to 1.75. Okay, so our z-score is equal to a plus 1.75. So we need to know what area is represented by a z-score of plus 1.75. Okay, well, obviously we're going to use our z-table. And I've also, I'm going to add these to the that additional files area on the class session so that you have this available. I'm going to do this two ways. First, I'm going to do it a very convenient table that came from another textbook called Agresti, okay, in which they actually, the z-score that they display here represents the area to the left of that z-score. So if you have a negative one, you're on the left side of the mean, so they're all less than 50%. See, none of them go over 50%, right? Highest is 50% for a z-score is 0, which is the mean. And if you get a positive z-score, right, it represents the area to the left still, but they're all greater than 50% because they're above the mean. So our z-score is 1.75. So that's going to be 1.7, and then 0, 1, 2, 3, 4, 5. If I scroll down, you'll actually see it. So that represents, I'm going to round that off again, 96% of the possible outcomes for the mean, 96%. So I'm going to go back here. So this area, this area represents 96%. So that leaves 4% of the means that you would obtain doing this repeatedly, right, would be above 33. Everybody comfortable with that? I got a question there? Yeah, exactly right. The question was, I want to verify standard error is another term for standard deviation of sample means. That's exactly what it is. Okay, so you can look at it either way. Just giving a special name to that one to distinguish it from the standard deviation of the distribution itself, the original distribution or the actual values. Now, let's do something interesting here. Had this instead been, let me draw it a little bit differently. Had this instead been the sample distribution of the population itself, well, the mean would have been 29.5, just like before, but the standard deviation would have been 9.25, right? So what's the probability now of getting an individual from this population, right, that's above a value of 33? Well, in that case, the z-score for the population is going to be, again, 33 minus 29.5, right, over the standard deviation 9.25 this time, not the standard error. And that's going to be equal to, I'm going to call that, it's 3.5 divided by 9.2, right? I'm going to say that's going to be roughly about 0.32 or something like that, 0.32. I'm not going to actually do the calculation. That's an estimate of 0.032. Now, if I go back to my table here and I look for what z-score of 0.03012, 0.032 is 63%, right? So that means the area to the right there is now 63%. So that leaves the area to the left to be 37%. So that the odds of picking an individual from this population and finding that they have albumin level above 33 is 37%. The probability of taking a sample of size 25 and finding that the average of that sample is above 33 is only 4%, much less likely because the distribution is not as wide. Okay, so that's basically what we're looking at there. And that's an illustration. That's one of the reasons why when you read these problems, you have to look at them analytically and very carefully and decide, am I working with the population or am I working with the distribution of sample means? And that's pretty critical to this. Next couple of parts, what proportion of the means are less than 28? What proportion of the means are between 29 and 31? Again, they're talking about means. So now you're going to go back and you're going to do the same thing we did. Proportion means less than 28, where you're going to take the standard, the difference between 28 and 29.5, 1.5, divide by its negative this time, 28 minus 29.5, it's to the left of the mean, divided by the square root by the standard error, right, to find the z-score, which is going to be a negative number, and then you're going to use your table to figure that out as well. And between those two values, you're going to do what we did before, which is figure what's the area below 29, what's the area below 31, and now find the difference between the two of them, which will represent the area in between them, right? It helps to sketch it out, perhaps a little bit more neatly than I sketched it out, but it definitely helps to sketch it out so you don't make any mistakes in terms of figuring what area that you're working with. Hopefully, I'll come across one. I don't want to get too bogged down on this one problem, but at some point or other, I'll work with this and see where the and see how we take a look at these. In case it's important to you, see how we figure out the areas between a couple of these values, because that might be an issue for some people. I also just wanted to bring up one other thing, and that is just want to show you what it looks like if I use the table in your textbook instead of this table. I'm going to close this for a moment. Table in your textbook looks like this. You only get a single table, right? Which is okay because all the values are represented here. When we looked up the value 1.75 for the z-score, that would be 1.7012345, which is 0.04, 4%. Well, what that's telling us is that's telling us the area to the left, the area in the upper tail of the standard and normal distribution. In other words, actually the area that we were in fact looking for when we did this, right? Which was the area that's up here, the 4%. So we get it right away. So that the first table we looked at gave us the area, if we put the z-score in, it gave us the area to the left of the z-score. The second table we looked at gives us the area in the upper tail. So if you're looking for the percentage of samples are going to be above 33, it's going to be 4%. If we're using the first table, you got to figure, oh, well, the area below is 96%, leaving 4%. If I had asked you if we were looking at the opposite z-score, minus 1.75, the table would have given us the top 4% above a z-score of 1.75. And since we know the normal distribution is symmetrical, we know to the left of minus 1.75 is the same area as the area to the right of plus 1.75. Okay, so I killed a little bit of time on this particular example, but there's a lot of things here that were fundamental that are just going to come up over and over again. Okay, let's take a look at one of the next ones. Chapter 2, let's take a look at this one. In Denver, Colorado, the distribution of daily means of ambient nitric acid, a corrosive liquid, is skewed to the right. We know now that this is not a perfectly normal standard deviation, a population. It has a mean of 1.81 and a standard deviation of 2.25. Describe the distributions of mean of samples of a size 40 from this population. Okay, just a quick question. Okay, I'm going to leave that up to you. Size 40 we defined for ourselves as a large sample. We talked about the central limit theorem. Tell me just in 100 words or less, keep it concise. You're going to wind up telling me, well, what do you know about the distribution of the means, given that it's a large sample size? Okay, I think that's enough of a hint there, right? Okay, so let's take a look at the next one, Chapter 9. Before beginning a study, I got to move something out of the way here so I can see it. Before beginning a study investigating drug prevent bronchoconstriction, baseline values of pulmonary function were measured for a sample of 12 individuals with a history of exercise-induced asthma. The mean sample of 12 individuals, talking about small sample, with a history of exercise-induced asthma. The mean value of the forced vital capacity for the sample is 4.49 liters. Standard deviation is 0.83. The mean forced expiratory value in 1 second, FEV1, is 3.71 liters, and the standard deviation is 0.62 liters. Just so that we understand what we're looking at here, FEV1 is the volume of air. If you ever taken a pulmonary function test, basically what they make you do is blow into a tube and it measures the volume of air that you're exhaling. If you have obstructive lung disease, it's hard for you to, it reduces the amount of air that you can expel with each breath, and it also reduces the speed with which you can expel it. So there's two important values here. FVC is the total amount of air that you can expel. And if you've done this, you blow into the tube and they tell you to keep blowing, until you're blue in the face, and then they measure how much the total amount of air came out. The other important thing is because they're looking at restrictions in airflow, is they're looking at how fast you can blow that air out. FEV1 represents how much of that 4.49 liters, for instance, comes out of your lungs in the first 1 second. As you can imagine, if you're blowing air very quickly, most of the air is coming out very quickly, and then a little less and less and less over time is coming out. So FEV1 is what comes out in 1 second, an important measurement for understanding whether or not you have asthma or some other obstructive lung disease. Compute a two-sided 95% confidence interval from U1, the true population mean for FVC. Rather than a 95% interval, construct a 90% confidence interval. They just ask you to do it again for 90% confidence. Next part, compute a 95% confidence from U2, the true population mean FEV1. And in order to construct these confidence intervals, what assumption is made about the underlying distributions of FVC and FEV1? Okay, so now there's a couple of things going on here. And one of the things is that I just want to take a quick look here at Chapter 8 and see if we covered T-scores. Let's see. They mention if let me see. Chapter 8, we covered T-scores at that point, because it's going to be an important distinction here. Application central limit there. I don't think we've really gotten into T-scores yet. So first of all, I'm going to answer question D first. Sorry, excuse me for moving away from the screen there for a second. I'm going to answer question D first. And that is, we know that the central limit theorem will take a distribution that's not normal, right? A population distribution that's not normal, and give you a sample distribution which is normal, even though the underlying population distribution isn't normal, if you take large sample sizes. Okay, so problem here is that we're taking a small sample size. We're only taking samples of size 12. So in order for us to just assume that these distributions are normally distributed, our assumption has to be that the underlying distribution is normal as well. When we move on to some of the other problems, I'm going to assume that we haven't covered T-score in this yet. We move on to the other problems. We're going to see that, well, gee, in order to, if I can't assume the underlying population is normal, right, well, then I have to make some adjustments, and those adjustments are made with the T-score. So for the moment, I'm going to assume that the underlying population is normally distributed, and you're going to need to tell me that. in Part D in order to justify the answers that you've given me previously. So how would I do this? Compute a two-sided 95% confidence interval from you, the mean for forced expiratory value. Okay, let me get this out of the way. I'm going to get a fresh sheet of paper here. And, oops, wrong direction. And I'm just going to quickly look at the chat file to see if anybody's asking me questions. Not yet. Okay, good. And let me go back here. So our mean, let's see what we got here. Okay, so our mean was for FVC, X bar 1. Notice X bar 1, we're using X to represent our mean, is 4.49, I think it was, yep, 4.49. And our standard deviation, notice I'm using standard deviation, is equal to, standard deviation is 0.83. Okay, so now I'm going to take a sample size of 12. And if I assume the underlying population is normal, right? Well, then the distribution of the means of samples of size 12 should be normal also. Okay, I can assume that because the underlying population is normally distributed. So the mean of my population samples is going to be 4.49, and the standard error is going to be equal to 0.83, my standard deviation, divided by the square root of n, which is going to be equal to 0.83 over the square root of 12. Okay, this one I'm actually going to calculate out so that we can see how it works out. So let's see. The square root of 12 is equal to 3.6 whatever. I'm going to store that in memory. Okay, store that in memory. I'm going to clear this. And I'm going to say, okay, standard deviation is equal to 0.83 divided by, and I'm going to recall that number, and that's equal to 0.24, I'm going to call it. 0.24. Okay, so let's see. 0.24. So now I want to know what my 95% confidence interval is. Well, my 95% confidence interval, right, is going to be equal to, the mean for the sample distributions, right? Sample distribution means, okay, plus or minus the 1.96 times my standard error. Okay, why 1.96? Any opinion on why I'm using 1.96 there? Somebody? Why am I using that? Where that in 1.96? Well, I know in normal distributions, right, that 95% of the values for my means in this case are going to be between approximately 2 standard deviations below the mean and 2 standard deviations above the mean, plus or minus 2 standard deviations above, 2 standard deviation but below. In this case, in the case of samples, 2 standard errors above and 2 standard errors below. And actually, instead, the actual more precise value, if you look at your table, is really minus 1.96 standard deviation and plus 1.96 standard deviations. I'll even show that to you. Let's see if we can't check that out, if we can prove that to ourselves. Okay, let's take a look at 1.90, 2, 3, 4, 5, 6. 97.5% of these values are to the left of that standard deviation. That means that 2.5% are in the tail. So you got 2.5% in the upper tail, 2.5% in the other lower tail. So that's 5%. That leaves 95% between minus 1.96 and plus 1.96. Right? A little bit more precise than just using that 2. Okay, so let's see what's that going to come out to be. Confidence interval is going to be equal to our means 4.49, 4.49 plus or minus 1.96 times my standard error, which was 0.020, 0.24. Okay, so let's resolve that. Okay, and we're going to resolve that. We're going to see that, let's clear all this. So it's 1.96 times 0.24. This whole part is equal to 0.47. By the way, in certain situations, that's called the margin of error. So I'm going to put that into memory. Okay, and I'm going to clear this. So our confidence interval is going to be equal to 4.49 minus that value, the error, and it's going to be equal to 4.02. And the upper limit for our confidence interval is going to be 4.49 plus our margin of error, which is going to be 4.96. So we're 95% sure, based on this sample size from the sample size that we took, that the true population, remember, that's what we're really after. What's the true mean for the whole population of FVC? We're not interested in this sample. We're really interested in using that sample to determine the real population mean. Well, we think it's around 4.49 because that's what our sample came out being. But because we want to be able to quantify how confident we are about this, we calculate a confidence interval. So now we can say not just that we think it's around this number, but more precisely that we believe we're 95% sure that it's between these two numbers, right? So we have a little bit more power with that. Okay, let me just check questions. If you don't have standard deviation population, then use the standard error divided by. Hang on a second there, Rebecca. Let me point something out. I understand what you're saying. I didn't use the standard error. Excuse me. What did I just do? Oh, I'm sorry. I got it right. Your question kind of confused me for a second. Keep in mind, when they did this study, they didn't tell us the standard error. They told us that the mean for these 12 individuals, FEVC, the mean FEVC is 4.49. And they also told us the standard deviation for those 12 individuals, not a sample, not 12 samples, but 12 individuals. That standard deviation for those 12 people is 0.83. Just like the mean the mean of the sample estimating the population mean, the mean of the standard deviation of those 12 individuals estimates the standard deviation of the entire population, right? So we still got to divide by the square root of the sample size to change that into an estimate of the standard error. Does that make sense to you? In other words, they didn't give us the standard error. They gave us the standard deviation, not of the population, but of the particular sample of 12 people. So, and that's we're using, since we don't know the standard deviation of the entire population, we're using that to estimate the standard deviation or spread of the entire population. That's an excellent question. I'm glad you pointed that out because there can be some confusion with that. The next part of this, they asked me to calculate a 90% confidence interval for the same thing. Well, 90% confidence interval, the only difference between 95% confidence interval and 90% confidence is that we're willing to be less certain that we actually capture the population mean. So we're willing to use a z-score that's smaller because 90%, you wouldn't have to go 2 standard deviations out in either direction. You'd have to go out far enough that you have 5% in the upper tail and 5% in the lower tail, and that would represent a z-score of, let's bring that table up. That would represent a z-score of, well, I'm going to use this z-score table backwards. What would represent 95% of the area of the distribution? Well, look, it looks like it's right around here, 94.95, 95 point, a little bit more than 95. So it looks like it's right around here. And what value z-score represents a tail on each side of or 90% within those two boundaries. Okay, 1.60123. I'm going to use this one right here. That's good. It could be either one. I'm going to use that one. It's the first one I came across. So a z-score of 1.01234, 1.64 represents my 90% confidence interval. So instead of using 1.96 to calculate my confidence interval, I'm going to use 1.64. And that's going to give me my 90% confidence interval. Okay. If I want a 99% confidence interval, later on when you look at your z-table, you're going to notice that it's going to be 2.58. You guys can check that for me later on. So notice, if you want to be more confident that you have the true population mean within these two numbers that you predict, in order to increase your level of confidence, you have to make the interval wider. And the interval becomes wider because the z-score that you're using to represent that range gets bigger. You're multiplying by the standard error by a bigger and bigger number, the bigger the level of confidence that you want to have about being right about it. Okay, so I'm going to leave the other parts of these problems, the other part of that problem, which is basically just repeating what we just did, except using the FEV1. I'm going to leave that up to you guys. Let's take a look at this next one. Data set, low birth weight contains